Hi, my name is Shimant Misra, and this is my video lab report for Intro Physics 2211 at Georgia Tech. This lab examines the motion of two colliding objects. I'll first introduce some key ideas, formulas, and diagrams. I'll then analyze a collision in Tracker and construct a computational model to model the situation. Finally, I'll analyze the results from the model and my observed data and answer some key questions about the lab. So some of the key ideas explored in this lab are listed here. I use Newton's second law and the momentum principle to iteratively predict the motion of the two objects by assuming that the net force acting on each of them is zero except at the moment of collision. I also consider the conservation of momentum and conservation of kinetic energy to answer the discussion questions at the end of the lab. Another key idea is the difference between elastic and inelastic collisions. In both types of collisions, momentum is conserved. In elastic collisions, kinetic energy is also conserved, but in inelastic collisions, kinetic energy is not conserved. Finally, I'll be using a multi-particle system throughout my analysis, as I will be simultaneously tracking and modeling the position of two objects. So here are the formulas I used. I won't go into detail on each one as they're all formulas we've seen before, but very quickly I used the first two formulas in the GlowScript code to update the two objects' positions and velocities. I then used the bottom four formulas to determine whether or not the collision is elastic or inelastic. And why do we care about determining whether a collision is elastic or inelastic? Well, one example of their real-life applications include the design of automobile safety systems and the development of safer vehicles thanks to a better understanding of how collisions affect the occupants of a vehicle. So here's a diagram of my setup, in which I rolled one ping pong ball towards another, identical stationary ping pong ball, and recorded their x and y positions. So initially, ball 1 has non-zero momentum and ball 2 is stationary. During the collision, some of ball 1's momentum and kinetic energy is transferred to ball 2, resulting in them both having non-zero momentums at the end. In other words, they are both in motion at the end. I used this video I recorded and plotted the x and y positions in Tracker for each ball. I chose my axes such that positive x points to the right and positive y points upwards. Here's an excerpt from the code I wrote. I first created the two objects in the program and defined the origin. I then wrote the code for the two graphs, which we'll see later. After that, I set the initial conditions. The balls were identical and therefore had the same mass. I pulled their positions from the tracker data. Ball 2 is initially at rest, so has zero velocity. I found ball 1's velocity by looking at the first few frames of the video up until the collision and using those data points to calculate the average velocity of ball 1 and then setting that as my initial velocity. In the calculation loop, as mentioned before, I assumed the net force acting on the two balls is zero. I then applied the momentum principle using the two formulas shown here to update the ball's position and velocity. Finally, I plotted the ball's position on my graphs. Notice here that the loop only goes to 0.25 seconds, which is not the entire video clip. This calculation loop handles only the motion before the collision. To model the motion during and after the collision, I had to reinitialize the two balls' velocities, which I found using the same method as before, calculating average velocity and setting it equal to the initial velocity. After that, the second calculation loop is identical except for its time bounds, which now span the entire duration of the clip. Here's a video of the program in action. The first graph shows the x position versus time of both the balls, and the second graph shows the y position versus time. Ball 1 is blue and ball 2 is red. So now let's take a look at the results. I've graphed the x position versus time and y position versus time of ball 1 and compared the predicted and observed motion. As can be seen, the x position graph models the motion fairly well, except for some deviation following the collision. This is likely due to the ball slipping slightly following the collision and could be improved by using better balls, such as pool or billiards balls. The y position graph is slightly off for the entire duration. This is likely a computational artifact or an error when using Tracker, and could be improved with higher quality slow motion videos and better tracking software. Here are the same two graphs for ball 2. Ball 2 probably slipped even more than ball 1 as it was originally at rest, thus explaining the larger discrepancy in position values, both x and y, following the collision. The same improvements mentioned before would also help here. Now to answer some questions about the lab. The first one being, is momentum conserved? Well, I calculated the initial and final momentums, and what I found is that momentum is only somewhat conserved. There are fairly small yet significant reductions in momentum both in the x and y directions, but on the whole it's not too bad given the constraints we were working with. The reduction in momentum is likely down to a dissipation of energy by friction, reducing the speed of the balls and hence the momentum of the system. And now the most important question, is the collision elastic or inelastic? Well, looking at the initial and final kinetic energies, it becomes apparent that kinetic energy is not conserved. In fact, more than 50% of the original kinetic energy is lost in the collision, making this collision most definitely inelastic. This was in fact expected, as perfectly elastic collisions are rare, if not impossible, in real life. Thank you for your time and have a nice day.